In this video, we'll take a look at predicting kinetic and thermodynamic products. So before we get into specific questions, let's define a little bit about kinetic and thermodynamic products. So first of all, kinetic products are a 1-2 addition product. And what this means is whatever you're adding to your starting material, they're going to be added to carbons that are adjacent to each other. So if it was in a naming convention, it would be 1, 2 directly next to each other. Carbon 1 and carbon 2 have a new atom bound to them in the kinetic product. And mechanistically, kinetic products form through the most stable intermediate, or at least the more stable compared to the thermodynamic intermediate that leads to the thermodynamic product. This isn't always the case, but it is usually the case, and explains why we call the kinetic product the kinetic product, because that simply means it is the one to form the quickest by rate determination and things of that sort. So that is the kinetic products. Now let's talk about thermodynamic products. Thermodynamic products are 1-4 addition. Again, this is referring to the position of the starting material that you've added the new atoms. So in 1-4, now whatever you've added, whatever two atoms are at the carbon 1 and then carbon 4. And I should mention, like, if you were to consider this in nomenclature, it's not necessarily that the first carbon of whatever your IUPAC name would give you is going to be where it's added. It's just that the additional atoms are 4 carbons apart. They're on 2 carbons that are 1 to 4 in a chain. So that'll make more sense with an example, but that you will see 1-4 addition, and that refers to thermodynamic products. And the difference between kinetic and thermodynamic is the thermodynamic product forms the more stable final product, usually through a less stable intermediate, like was mentioned in the kinetic portion of the introduction. All right, here's a specific example where we would have a kinetic and thermodynamic product that are forming, and depending on the conditions, one of those sets will predominate as the products. So here we have a conjugated diene, conjugated because we're alternating pi bonds and sigma bonds, so pi, sigma, pi. And it's a diene because there's 2 alkenes, and it's a cyclic diene to be more specific. And then we have HBr, that is a typical strong acid, and we have, so that means that proton is extremely acidic and therefore electrophilic. So this is a typical electrophilic addition to a conjugated diene. So the mechanism is really no different than a typical electrophilic addition, where you would just have 1 alkene. The complication comes in that you have multiple alkenes to do the same type of chemistry, and you will have to look to see, mechanistically look to see which one is going to form and why. So first, it doesn't matter which alkene you start with. Both of them are going to react with the hydrogen. So recall, this hydrogen is acidic because, in part at least, because there is this dipole between the hydrogen and the bromine, which is therefore making this proton partially positive, which is susceptible to a nucleophilic attack. And then we have our alkene, which is electron-rich region that can attack the proton in an electrophilic addition type mechanism like it's shown here. This will form Br- as a byproduct, and it's going to add our hydrogen to one of the carbons involved in that double bond. So if we considered the hydrogen to add at this terminal position, so let me number these carbons, let's call this one 1 and this 2. If the hydrogen were to add at position 1, it would put the carbocation at position 2. And if it were to add at carbon number 2, the hydrogen, that would put the carbocation at position 1. Right, so the hydrogen is here in this case, and the hydrogen is here in that case. So if we were to rank these carbocation stabilities, this is a tertiary carbocation versus a primary carbocation. The tertiary carbocation is far more stable because of the added stability of all the alkyl chains can donate their electrons, some of their electrons at least, to the carbocation and stabilize it through a phenomenon called hyperconjugation. So because of that, there is no formation of this product, so we can just exit out. This will not form at all because it is extremely unstable compared to the alternative. Now, this isn't just tertiary, it's a tertiary carbocation that is also allylic, meaning that it's adjacent to a double bond. This is important because it means that that carbocation is stabilized by resonance. And the resonance form that occurs after this bond delocalizes, the pi bond delocalizes, is going to give us another carbocation that could lead to a different product, which is going to be important in the thermodynamic case. So, but before we get to that, let's finish what this product would give us. And we had Br minus as mentioned, which was formed in this initial step where the electrons get dumped onto Br and we have a Br minus as a byproduct. This bromine ion will attack the carbocation here, and this will give us one of the final products, one of the kinetic products. So we get this molecule here, and I'm going to continue showing just the one hydrogen that was added in the first part of the mechanism, because this explains why we call this a 1,2 product, because the hydrogen, depending on what you look at, it doesn't matter. The bromine and hydrogen are adjacent to each other on adjacent carbons, so this would be 1,2 addition, hydrogen at 1, bromine at 2, or vice versa. If you call this carbon 1, you put the bromine on 1 and the hydrogen on 2, so it's a 1,2 product. So this is one potential kinetic product. But now let's talk about the resonance that could form here. So again, resonance structure is double arrows, not equilibrium arrows. And if this were to form, you would delocalize these electrons here, forming a new pi bond, and it would put the carbocation at this position because we've moved the electrons away from that carbon. So that product is going to look like, or that intermediate, I should say, is going to look like this, where we put the carbocation here, right, which is this position. Now notice, this is secondary now. This is secondary and allylic. So that is less stable than our tertiary allylic position that we started with. So there is no driving force, there's no energetic driving force for this resonance to form. So that is in part why we call this the thermodynamic product or the thermodynamic pathway, because you need energy, high energy, to form for this unfavorable resonance to occur. So typically, we'll take a short aside here. So typically low energies for kinetic products occur less than 30 degrees Celsius. This is kinetic. And then above 100, say, it depends on the type that you have, the type of alkene that you have, but 100 plus is usually going to give you the thermodynamic product. So it all depends on the temperature. Otherwise, you could get very similar answers. So anyway, that is the intermediate that would form here. Then if you had a bromine attack, just like we did in the kinetic product, you're going to get the final product. And this now is going to be a thermodynamic product. A 1,4 addition or the thermodynamic product. And again, it's 1,4 now because if you look at this carbon where the hydrogen is, that's 1, 2, 3, 4. Hydrogen and bromine are on carbons 1 and 4 in the chain. So that would be a thermodynamic product. Additionally, this is a more stable final product because the alkene that forms here is tri-substituted versus this alkene in this product is only di-substituted. So recall that more substituted alkenes are more stable, and therefore this is further support that that's a thermodynamic product because it is more stable. But this is only the first double bond reacting. We have a whole nother double bond to consider, right? So let's redraw this reaction. So what we've shown so far is this first double bond reacting at that position, but we have a whole nother double bond. And there's no reason initially that it couldn't attack. So we're going to show that it would. And when it does, we get a different product, right? So here now, as we already mentioned, the carbocation has to go at this position because this is secondary and allylic. If it were to go at this position, at the other carbon, that would just be secondary, which is less stable because we don't have this resonance that stabilizes it. So because of that, this is the primary intermediate. And then, again, the bromine can attack. And when it does, this gives us the final product, or the kinetic. So here would be one kinetic product, or the other one, I should say. Again, this is 1, 2, because they're adjacent to each other on adjacent carbons. And then, of course, we can have the resonance, like we had in the last case, which in this, and once again, this is going to be not favored. So if this pi bond goes down there like that, we would get a different carbocation, like here. And then again, the bromine can add to that carbocation. Now you may wonder, is this really ever going to form? Because that's a primary carbocation, but it's primary and allylic. So yes, it will form. It's not extremely unstable because of the allylic nature. If you didn't have it allylic and it was just primary, then you would be right. And this is basically an irrelevant pathway because you're never going to form that intermediate. It's too unstable. But it's not the case here. So we get to the addition, and now this is again a 1,4 product, thermodynamic product, because we have the hydrogen at this carbon 1, 2, 3, and 4. There's the bromine, so 1,4 thermo product. In addition, the alkene is tri-substituted as well versus a di-substituted alkene, so the final product is more stable. So here's the same question again. I'm just giving a specific temperature, and we're going to go through this process once again, but a little bit expedited this time, and I'm going to point out some chirality importance that was not mentioned initially, just because I didn't want to overclutter the initial mechanism. So here what you should do is kind of make observations. You should always do this when you're looking at to predict the product or any kind of mechanism question, because the observations will help you if it's not clear to you how you're supposed to proceed. So the first thing that you should notice is it's a conjugated diene, which right away tells us that thermo and kinetic considerations are necessary. So once you notice that, then you notice that you have HBr. That again is a typical electrophile. The hydrogen is, so electrophilic addition should be on your radar. And then it's 25 degrees C, so this is going to be the kinetic set because this is a low temperature. Okay, so you don't have to worry about resonance or anything in this particular case because it's at such a low temperature. So with that then, we'll go through the mechanism again, a little bit quicker this time. So this attacks like so, and that gives us one of the possibilities. Again, the carbocation has to go here because that is far more stable position compared to the primary. And then the bromine now will attack the tertiary carbocation, and this will give us the product. This is one of the kinetic products. There's two. Now, this is the point I didn't make just to avoid clutter. So this is the 1,2 product, but this is also a racemic mixture because this position is now chiral. Notice there isn't symmetry here. It's broken by the double bond and the methyl group then. So the methyl group and the double bond here breaks the symmetry. So those are all different groups such that that is chiral. So this is a planar intermediate. So the bromine can attack from above or below. There's no preference. So because of that, 50% of the bromines available are going to attack from above, 50% will attack from below, and that's going to give you an anomeric mix of a ratio of 1:1, and that is hence a racemic mixture. So that is why we would get to this chirality. So now let's consider if the other double bond attacks. So if the other double bond attacks like this, that's going to give us this secondary option here, where the carbocation is going to go at this position, secondary and allylic. By the way, the hydrogen is here, which is why it's 1,2. just as a reminder. And then again, in this case, now we have our bromine floating around because it was removed as a leaving group there in the first step. So that bromine can attack and add and then give us, again, a racemic mixture of our kinetic product. So once again, racemic because it's a planar intermediate, and it's 1,2 because the hydrogen and bromine are adjacent to each other in a 1,2 fashion like this. So this would be the complete answer for this question. You would have to include both of these because there isn't a drastic difference in the stability of those intermediates. The tertiary and allylic position is far more stable, and it's going to be preferred maybe 60 to 70%, but you're going to get a significant amount, a non-negligible amount of this product. So you have to include that. You won't get any of the thermodynamic products in any significant contribution because the resonance forms are disfavored and the temperature is not high enough to allow for that disfavored resonance to occur. So these two answers would be sufficient and most accurate for this question. All right, so once again, here is the same question, just at a different temperature, again, which is going to change what the products are going to be. So these subtle differences have a major difference in what the correct answer will be. So again, let's make our observations. We have a conjugated diene. I'm not going to write it this time just to avoid clutter, but conjugated diene, high temperature, and we have electrophilic addition. So it's high temperature, so I will write down that this is going to be our thermodynamic products. So we have to draw the resonance forms, and those are going to drive the product if those resonance forms yield a more stable intermediate. So again, we'll start with the addition to our pi bond, like this. Right, now we have to consider resonance. I'm not going to draw the arrow just because I don't want to, like the resonance arrow, I don't want to show too much clutter there. But if that were to, on second thought, I'm actually going to show it, try to avoid confusion there. But if this were to move like that, it would put the carbocation at this position. So that is one possibility. And the bromine can attack now here. And this will predominate here because that intermediate, or not the intermediate rather, but the product is more stable. And this is also racemic. So this is a 1,4 product. It's racemic because we had a planar intermediate in the carbocation. So we'll get 50% of the bromines above the plane, 50% below the plane, and that will give us one of the products. Now, if this wasn't more stable, like if this alkene wasn't more stable, then there would be no reason for this to occur. So just keep that in mind as you're going through this. Sometimes thermodynamic considerations are unnecessary due to the nature of the molecule that you're looking at. But here they are very important, and they will dictate what is the product. So now let's consider the other double bond. So the other double bond, I'm going to draw it down here. Right, so if this happens as drawn in green, you would get this intermediate here. Again, this carbocation is more stable because it's allylic, and then we'll get resonance like drawn. Now in this case, it forms a primary, but it's also allylic, so it's sufficiently possible. And we form a more stable alkene, which is ultimately the driving force of the product formation. And then the bromine is now floating around. That can attack here, and this gives us the other product. Now, you cannot say that this is racemic because this is a chiral, right? Sorry, you couldn't see the hydrogen there. But this is again 1,4 addition because carbon here, 1, 2, 3, 4. But you can't say that this is chiral or racemic because that is not a chiral position here. You have two hydrogens that are breaking the what would be the chirality there. So you would just draw that as one possible answer and not call that racemic. but these two would be the 1, 4, and thermodynamic products. If the question was exactly as written up here, you would have to include both of them to get the most points, the most correct answer that is possible. So that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a question or suggestion, please feel free to leave it down in the comment section below, and I will get to it as quickly as I can. So with that, I'll see you all in the next video.